Hello everyone, I hope you are well and keeping safe in this second wave of COVID. Sorry for the long absence in videos because of the school work. Today's topic will be slanting squares. This topic will be useful for construction purposes. But first, what are slanting squares? Let us first check the area of the normal square. Then always the square of a number is basically that number times itself. For example, the square of 3 is 3 times 3 equals 9. For 3 squared equals 3 times 3 equals 9. The same thing is equal to any other number. If we put a variable a can be any number, and if we write squared, then that means a times a. So, for example, this equation can be used for most squares. For example, if I have a 3 centimeter by 3 centimeter square, its area will be 3 times 3 is 9 centimeters squared. Like here, 3 times 3 squared is 3 times 3 equals 9. And similarly, if this area if one side was 12 centimeters, then the area of our square would actually be 12 squared is 12 times 12. And if we do some calculations, we find that the area of 12 times 12 of this square if this square with 12 centimeters as one of its sides will be 144. So far simple, but some squares don't have these simple amounts like squares. An example is here. Assume that actually instead of just I do a 1 centimeter wave thing, except instead of just going down straight away and making a square that way, I'm actually doing the other side too, and then marking here and doing 1 here. So basically you could call this a 2-1 square. Let me just repeat this all around. And now if we connect these points, we'll have a square. But what's the area? First, let's calculate the area of the big square. Again, it will be 3 centimeters, and 3 times 3, as we know, is 9. Now let us find the area of the triangles. The area of any triangle is its height times its base times 1/2. The length of its height times its length of its base by 1/2. So the length of its base is 2 centimeters, and the area of its height is 1, and the length of its height is 1 centimeter. So we'll have 1 times 2 times 1/2, or 1/2. Now here we'll have 1 times 2/2 equals 1 times 1 equals 1. Since there are 4 of these, we'll have 4 times 1 equals 4 is the total area of these squares. And then we have 9 times 4 equals 5 squares. Now of course we know that 3 squared equals 3 times 3 is 9, but 2 squared will be 2 times 2 is equal to 4. So notice that 5 is neither 4 nor 9. So we've actually got a number which is different from these squares while still drawing a square since it's slanty. And what is the area of these squares? So first, let us calculate the area of the big square. Of course, the area depends on just one side. So here, notice that we can replace this with a, the bigger one, the bigger variable, and b will be the length of the smaller side. And these go all around. So the side of 1 will be a plus b. And since the area of any square is this length squared times itself, then this will be a times b, a plus b squared. Next, we need to subtract the area of all these triangles. Again, this will be the same equation. The area of a triangle is its height times its height times its base times 1/2. So that since there are 4 of these, we'll have 4 times 1/2 plus 4 times 1/2 times a times b. In algebra, these two will be together, so this is ab. So now we have 4 divided by 2 will be 2, of course. So in overall, the equation will be a plus b squared minus 2 times a times b. Now this together will be 2ab, by the way. And now let us work out the square. There's this method called FOIL actually, which can help us to do this. First, we'll have to write it like this. The a plus b squared. So a plus b bracket times a plus b bracket. So then we'll have here, first we're going to multiply these two, a and b, a and a. So we'll have a times a, which is equal to a squared. Next, we'll have the outer and the inner. So we'll have a times b and b times a. Together, they will be ab and ba. Since they both are just changes in the order of the letters, then the product will be the same. So we can write both of them as AB. Now notice that these two are the same. So AB plus AB is of course going to be 2 times A times B, which is the same as this. This will come in important later. Lastly, we have to multiply these two. So we'll have B times B is B squared. So in all, this entire thing, A plus B squared is going to be A squared plus 2 times A times B plus B squared. Now we'll of course have to subtract 2AB, but look, these two are matched, so we'll have to cancel them. But now, with A squared plus B squared, and for those who can see, let us just check it works. So the area of this the length of this small side is 1. So 1 times 1 is equal to 1. And by the way, this is equal to 1 squared. Now 2 squared is equal to 2 times 2 equals 4. Because the area of A, the bigger side, is 2. So this is 4. Now if we add 1 plus 4, it will equal to 5. Have you noticed what you have proved? If I just write here C, and if this were a small square and this is a large square, sorry I did a rectangle, but still, we've just proved Pythagorus Theorem. A squared plus B squared equals C squared. So basically, the area of these two squares, or the square of one side plus the square of the other side, is equal to the area of this base square. This is a direct proof of Pythagoras Theorem, and by far my favorite, because it arises out of a problem, and from it we are getting a proof. Now the next question is, with this slanting method, can we get every number No, and the proof of that is in this thing. Only a squared plus b squared numbers can work. Of course, you may be asking, then how come 16 will work and 9 and all those other square numbers? Because they really do work by the Pythagoras Theorem. You just need to be a bit more creative. For example, for 16, that is 4 squared plus 0 squared. 0 times 0 is equal to 0, and 4 times 4 is 16. And adding 0 to anything does not change it. So overall, this is 16. This is how the square numbers work. But some numbers, even with the slanting thing, you just can't work out. An example of these numbers is 3. You just can't take the sum of 2 squares and get 3. Even 1 squared plus 1 squared, that is equal to 1 plus 1, because it's 1 times 1 times 1 times 1, and both of those are equal to 1. And if we add them together, we get 2. And if we try 1 squared plus 2 squared, then 1 plus 4 is equal to 5. We've got 5 here. But as you can see, this just doesn't work. 2 squared plus 0 squared is again 4 plus 0, which is equal to, 4. So this shows that we just can't get 3, no matter how hard we try. We have to go for fractionals, and here we can't allow the fractionals. So this is the best we can do for 3, 4 or 2. The application of this is because of the proof of the Pythagoras Theorem. It helps us to make these triangles and these slanting squares. For example, this might be useful for things like solar panels, which are made of rectangles, and rectangles are just twice the area of triangles. For example, this thing is a rectangle and it's made of these two same triangles. And it will also be useful in a building which is made out of a lot of squares, which happens mostly in modern cities. That's all I have to say.